Good morning, students. Our today's topic is Reisz lemma and its applications. Reisz lemma states that for the two subspaces Y and Z of a normed space X, where X is of any dimension and Y is closed and is proper subset of Z. Here this is our normed space X and Z and Y. These are the subspaces, and we can see here that this Y is proper subset of Z. Then we are to prove that for each real number theta lying in the open interval 0, 1, there exists an element Z belonging to the subspace Z such that the norm of existing element is 1 and the norm of Z minus Y is greater than or equal to theta for every Y belonging to the subspace Y. So we are to prove these three conditions. Firstly, we are to find an element Z from the subspace Z, then show that its norm is 1, and then we show that the norm of Z minus Y is greater than or equal to theta for all elements Y belonging to the subspace Y. Now, because Y is proper subset of Z, so we can take an element V which belongs to Z but does not belong to Y. It means we can say that V belongs to Z minus Y. Here we can see this element we have taken as V. This element is in the set Z, but it is not lying in the set Y. Now, let us take the distance between the set Y and the element V is denoted by A. By definition of distance between a point and a set, this is given by the infimum of the set of the distances of all the elements of Y from V. Now, clearly this distance should be positive because if this distance is 0, in a metric space, if the distance of an element from a set that is 0, then that element belongs to the closure of that set. Now here, if A will be 0, then it means the distance between the element V and the set Y, that will be 0. It means by the property V will belong to Y closure. Because Y is closed here, so Y closure will be same as Y. So it means V belongs to Y. But that will be a contradiction because we have taken V belongs to Z minus Y. So A cannot be 0. It means A should be positive. Now because theta belongs to the open interval 0, 1, so A upon theta, that should be greater than A. Now because A is the distance between V and Y, so by definition of distance between point and set, A is the infimum of the set consisting of norms which are the norms of V minus Y. Here V minus Y norm, that denotes the distance between the element V and the elements Y of the set Y. Now, by definition of infimum, there exists an element, say Y0, belonging to Y, such that norm of V minus Y0 is greater than or equal to A and less than or equal to A by theta. Now we are to define an element Z which belongs to the subspace Z. So let us take Z is defined by the ratio of V minus Y0 divided by the norm of V minus Y0. Now clearly because V minus Y0 belongs to the subspace Z and this is a scalar. So this element Z belongs to the subspace Z. Now we have to verify the two conditions. First, the norm of this element should be 1, and second condition, the norm of Z minus Y should be greater than equal to theta for every element Y belonging to the subspace Y. So let us find the norm of Z. Substituting the value of Z here. Now because this is a scalar and in the numerator we have V minus Y naught norm. So these two terms are same. They will be cancelled out. So we get norm of Z is equal to 1. Now it remains to show that the Z minus Y norm is greater than equal to theta for every Y belonging to the subspace Y. So let us take an element Y belonging to the subspace Y and let us consider the norm of Z minus Y. Now substituting the value of Z defined by us already. So and taking LCM and taking the scalar outside. V minus Y naught norm, that is a scalar that we have taken outside after taking LCM inside the norm. Inside we get V minus Y naught minus Y into norm of V minus Y naught. Now we can take minus common from this expression. Inside the norm we have V minus Y naught plus Y into V minus Y naught norm. Now Y naught belongs to Y, this Y belongs to Y, and norm of V minus Y naught, that is a scalar. So this whole element belongs to Y, and also Y naught belongs to Y, and Y is a subspace, and that is closed under vectors addition. So we can say that the sum of these two elements also belongs to Y. So we can say that this expression, that is a vector in the subspace Y, and let us denote this vector by Y1. So we have denoted Y1 is equal to Y naught plus Y into norm of V minus Y naught. So we have obtained the norm of Z minus Y is equal to norm of V minus Y1 divided by norm of V minus Y naught. Now let us find V minus Y1 norm. Now because A is the infimum of the set of the distances of the elements of the set Y from the element V. So A will be, so this will be greater than equal to A. It means V minus Y1 norm is greater than equal to A, and also V minus Y naught norm is less than or equal to A by theta. Taking reciprocals, we get 1 upon V minus Y naught norm is greater than or equal to A by theta. So substituting the values here, we get Z minus Y norm is greater than or equal to theta. Thus we have proved all the three conditions, and this completes Reisz lemma. Now we will do one of the applications of Reisz lemma. We already discussed in a finite dimensional normed space the closed unit ball that is compact. Now we will prove its converse by using Reisz lemma. So its converse is given by the following theorem, which states that if a normed space X has the property that the closed unit ball is compact, then we prove that the space X is finite dimensional space. We will prove it by contradiction. So let us suppose the dimension of X, that is infinite, and let us take a non-zero element belonging to this norm space X, and we define a vector x1 obtained by dividing X by its norm. Now we can see that the norm of this element is given by Norm of x1 means norm of x divided by x norm. So this will become 1. It means norm of the vector x1, that is 1. Now let us take x1 be a subspace of norm space X, which is generated by this element x1. Now because the dimension of x1, that will be 1 in this case, so we can say that x1 is finite dimensional. Now we already discussed two results which we use here. First result, every finite dimensional subspace of a normed space is complete. Now because here x1 is finite dimensional subspace of X, so by this result x1 is complete. Now the second result which we'll use is a subspace of norm space X is complete if and only if it is closed in X. So by using this result here, because x1 is complete, so by this result x1 is closed also. Now we are in a situation to use Reisz lemma. Now to use Reisz lemma, we require two subspaces of a norm space. One of them should be closed and proper subset of another. So here x1 and x, these are the two subspaces of the normed space X. And also we have proved x1 is closed and x1 is proper subset of X, because the dimension of X is infinite and the dimension of x1, that is 1. So we can apply Reisz lemma. So by that lemma, for every real number theta lying in the open interval 0, 1, there exists an element x2 belonging to the normed space X such that the norm of this element is 1 and the norm of x2 minus x1 is greater than or equal to theta, because theta lies in the open interval 0, 1. So let us take in particular the value of theta is equal to 1 by 2. Now let us take these two elements x1 and x2, they generate the subspace x2. Because x2 is generated by the two elements, so we can say that the dimension of x2, that is 2. And again by using the same property as we used for x1, we can say that this x2 is closed. And again we can use Reisz lemma. So by using that lemma, for each real number theta lying in the open interval 0, 1, there exists an element x3 belonging to M such that the norm of that element is 1 and the norm of x3 minus x, that will be greater than or equal to 1 by 2. This element is from X here. In particular, because this condition is true for all elements X belonging to x2. Now because x1 and x2, they also generate x2. So in particular, we can use this condition for the elements x1 and x2. So this condition will become the norm of x3 minus x1 is greater than or equal to 1 by 2 and norm of x3 minus x2 is greater than or equal to 1 by 2. Now proceeding by induction, we get a sequence xm in M such that the norm of xm minus xn is greater than or equal to 1 by 2 for every m and n which are different. And obviously the sequence cannot have a convergent subsequence, but that will give us a contradiction to the compactness of M. So it means our assumption is wrong, which we have assumed that the dimension of the norm space X, that is infinite. So this contradiction proves that the dimension of X should be finite. So this was one of the applications of Reisz lemma.